Hey, Tree class, we're going to look at 10.5, the dot product of two vectors. So in the previous video, or previous section, we learned how to add vectors, subtract vectors, scale vectors. That was kind of multiplication, but this is a way to multiply two vectors. There's actually two ways. We don't get into the second way in this course, but the dot product of two vectors is actually going to give us a scalar, and that scalar leads to the idea of the angle between two vectors. That scalar has something directly to do with the angle between the two vectors. Alright, this is the definition of the dot product. So if I have two vectors, the dot product of those two vectors is multiplying those horizontal components together and then also multiplying the vertical components together and then finally adding those at the end. Alright, so x component of the first vector times x component of the second vector, y component of the first vector times y component of the second vector, and then the sum of those. So this is a number. Multiplying numbers gives numbers, adding numbers gives numbers. This is just a number. So the dot product of two vectors is a scalar, not a vector. Right, let's just use the formula real quick. 4 times 3, the x components, is 12. Negative 2 times 2, the y components, negative 4. 12 plus negative 4 is 8. Right, if I reverse it, w dot v, well, now I'm multiplying the second x first, so that's like 3 times 4, and 2 times negative 2. It's still 8. The order that we do the dot product does not matter. All right, dotting v with itself. That means I'm going to multiply the 4 times itself, the negative 2 times itself, and add those. So I'm going to get 16 plus 4, negative times negative positive, that's 20. All right, this is actually the magnitude of the vector squared, which we'll see in just a second. All right, w dot w, same thing. We're going to square the 3, we're going to square the 2. That's going to give us 13. And then the magnitude formula. Notice all we're doing here is what we did on part C, but without the square root. So the dot product of a vector with itself is always going to be the square of the magnitude. So when we multiply two things together and get out a number, we call that a scalar. So oftentimes the dot product is referred to as the scalar product. So what we saw before is that the order you do the dot product doesn't matter. There's a distributive property that says I could find the resultant of two vectors and then take the dot product. But what happens here is that's the same as if I took the dot product of each vector with the u on the outside and then found the resultant. So it's literally like you think of when you were a kid and there were numbers. That's the distributive property. It's just these are vectors now. So I'm dotting the outside vector with the first on the inside, dotting the outside with the second on the inside, and then adding those two vectors. Well, they're not vectors, they're numbers because they're dot products. We saw that property just as well. Dotting a vector with itself is the square of the magnitude. And then if you dot any vector with the zero vector in any order because it's commutative, you're going to get out the number 0. Right, remember the zero vector is a 0, comma, a 0. That's the zero vector. So when you do that dot product definition, you're multiplying 0 times the x component of v. And then you're multiplying 0 times the y component of v. So you're obviously going to get 0 there. All right, what does the dot product tell us? Well, when the dot product is positive, what that tells us when we talk about the angle between two vectors, it's always the smallest angle between the vectors. So if I have these two vectors, this is the angle I'm talking about. I'm never, ever, ever going to be talking about this angle, right? So that's like angle number 2. That's never going to be the angle that I'm talking about. It's always the smaller of the two. And because of that, the biggest it could be is 180 degrees. And that's like 0 to pi radians, right? That's like quadrant 1. So we're never going to get an angle bigger than that. If my angle between the two vectors is acute, so it would like fit into quadrant 1, I could kind of readjust the two vectors wherever they might be positioned. Position one of them on the x-axis, and the other one would be out in quadrant 1 somewhere. If it's acute, the dot product is going to be positive. But if I have an angle that takes me into quadrant 2 when I put them together, now the dot product is going to be negative. So if you think about it, there's a trig function we know about that's positive in quadrant 1 and negative in quadrant 2, and that's the cosine. And what we're going to see is in this slide, the angle between two vectors is going to be found by the cosine. The cosine has to do directly with the dot product. So here is how we're going to find it. the cosine of the angle between the two vectors, that is the angle between the two vectors there, that theta, is equal to the dot product of the two vectors divided by the product of the two vectors' magnitudes. So if you give me any two vectors, I dot them, I divide by their magnitudes, inverse cosine will give me that angle between the two vectors. Remember, inverse cosine is defined between quadrants 1 and 2. So if it's in quadrant 1, it's an acute, cosine can find it, inverse cosine can find it. If it's in quadrant 2, it's obtuse, and inverse cosine can find it. So the first thing we're going to do to find the angle is to find their dot product and the two vectors' magnitudes. So the dot product's easy enough, just multiply the x components, the y components. There's my dot product. It's negative. That means this is going to be an obtuse angle when the dot product is negative. The magnitude is the square root of 20, that's 2 square root of 5. Magnitude of v is the square root of 34. That cannot be simplified. So when I type this into my calculator, it's fine just to leave it as the square root of 20, because when you type it in there, you're going to approximate it and use the inverse cosine on that whole expression anyway. So we get roughly 94 degrees as that angle between the two vectors. They'll usually have you round these to a whole number angle, but just pay attention to the rounding that they tell you to use. All right, we've already talked about vectors being equal, but if they're not equal, if one is a scaled version of the other, then we call those vectors parallel. So two vectors are parallel if there's a scalar that I can use to go from one to the other. Right, and again, you can scale a vector and negate it. So right, that's that's w. If I scale it and negate it, meaning I go back in the other direction and make it longer. If I make it longer, so I've scaled it, but I'm in the opposite direction, so it's a negative number. That's fine too. That's still parallel. So it's any value a alpha that's not 0. So it could be negative and not be 0. So point it in the exact same direction or in opposite directions, and one's just longer than the other or in the other direction, then those vectors are parallel. All right, another way to say it is the angle between the vectors is 0 if they're pointed in the exact same direction. So one's pointed this way and so is the other one. If they're pointed in the exact same direction, the angle between the vectors is 0. But if they're pointed in the opposite direction, the angle between them is going to be that pi radians. All right, I can see that these vectors are parallel because the number it takes to go from 6 to 8 is the same number it takes to go from -3 to 4, which is dividing by 3/4 or multiplying the other way by 4/3. There's an easy to verify scalar there. And what you could do is just divide 6 divided by 8. Reducing that gets you 3/4, and divide -3 divided by -4. That's the same thing. That's 3/4 also. So I can see that I am multiplying one vector by the same thing to get the other one. So that's a scalar. So that means the angle between them is going to be 0. But just to verify, there's the dot product. I get 60 over the square root of 3600. Well, the square root of 3600 is 60. So the cosine is 1, and the cosine is 1 when theta is 0. All right, determining two vectors are orthogonal now, because orthogonal is 90 degrees or pi over 2 radians. The cosine of pi over 2 is 0. So in this case, the dot product would be 0 if two angles are orthogonal, meaning a 90-degree angle between them. So when we do the dot product, what's going to happen is we're going to get a -4 here, a +4 here, and summing those together would give me 0. That implies these two vectors are orthogonal. All right, any vector can be decomposed into two orthogonal vectors. So what I mean by that is if I have a vector, there exist two vectors that I can use to combine together that are 90 degrees away from each other, or 90 degrees between each other, and adding those two 90-degree vectors will give me the vector I started with. So that's what decomposition into orthogonal vectors means. We start off with the red vector, and our goal is to find the green and blue vector that decomposes that vector. All right, so you can see the idea of decomposition. Here is an object sitting on a ramp. All right, gravity is pulling down on that object. That's kind of like the weight of that object itself. But because it's on an incline, it's on a ramp, that gravity pulling downward is going to do two things. Number one, it's going to pull the object down the ramp. It's going to slide down that ramp in the direction parallel to the ramp. But there's also this component that's keeping it on the ramp. It's orthogonal to that direction that the ramp the object's going to slide down the ramp. And so those two forces, F1 and F2, would combine. If I start with the F2 and added the F1, I'd get the F force. If I started with F1 and added the F2, I'd get the F force. So those F1 and F2 are the orthogonal components of F. So when we do this, when we come up with these orthogonal components, one of the two vectors is always going to be this idea of vector projection. And I like to think of it as if I've got a vector V in space, if I go to the kind of the center of it and imagine a light above it. So there's a light shining down on this. So the vector V, the shadow of vector V would be the shadow down onto this vector. And once I come up with that shadow of the vector V onto this shadow of vector W, I can just subtract. Vector V is what I want. I want these two things to sum to vector W. And V minus V1 would be this little V2 right here. And that's how I can find the two vectors. All right, so this is showing you two different variations here. This is if the angle between V and W is acute, and this is showing you if the angle between V and W is obtuse. That vector projection, V1 is the projection. It's going to be in the opposite direction of W. All right, but again, it'll be parallel, just kind of be an extension of that W vector. So this is like a little piece of W that this vector is, and this is in the opposite direction of it. So that first vector V1, this is how we find it. It's just this formula. It's a dot product divided by the magnitude of the vector that we're landing on. Okay, that's the magnitude of the W vector. It's the one we're landing on, times W. So this is basically the scalar. This is how long this piece of the vector is. So we're taking the W vector and we're scaling it up and down by this magnitude right here. So this is how we scale the W vector, but this, because we've scaled it, we're on it. So that's what we mean by V onto W. It's that shadow of the V vector onto W. And then once we found V1, there's how we found the orthogonal component. We just subtract V1 from V, and we've got that second vector that's orthogonal to it. All right, so here are my two vectors. I'm going to project V onto W and then find V2. Find the V2 vector from subtraction. So the first thing I'm going to do is that formula, the dot product of V and W divided by the magnitude of W squared, all that times the W vector. So again, the dot product of V and W, this is 2 times 1 is 2, 4 times 1 is 4, so 2 plus 4, that's just going to be 6. The magnitude of W, this is 1, this is 1. 1 squared plus 1 squared is 2. The square root of 2 is 2. So this is just the magnitude of W squared. You can also think of it as W dot W. We talked about that before. So 1 times 1 plus 1 times 1 would be just 2. So this is going to be 2 plus 4, 6 over 2. 6 over 2 is 3. So this is just, V1 is just 3W. And now we're just going to subtract. Now we take our W vector, which is ij, so that's going to be 3i plus 3j, and we subtract that 3i plus 3j from the original V vector, and we get that second vector. So this vector and V1 are orthogonal. You can multiply and see. 3i times negative 1, so 3 times negative 1 is negative 3, positive 3, positive 1, that's going to be a positive 3. So they're going to have a dot product of 0 every time. So they're orthogonal, and then if I add them together, 3i minus I is 2i, 3j plus j is 4j. They add to j. So that's what we mean by the vector projection. All right, so this is, again, there's V. If I shine a light on V, the shadow hits on W, and I have to extend W for the shadow to hit onto it. So it hits on it like that, and then that is the vector. That's the extension of W to get V1. We're tripling. We're having to make it longer for us to catch all of that shadow, and then turning this is a subtraction. The 2i plus 4j. If I subtract V1, this is the vector I get, and because I subtracted to get it, adding it to V1 means the resultant is V, and that's what we mean by the orthogonal projection. Okay, that's the idea of decomposition of a vector. I got two kids in a wagon. There's 100 pounds total with the two kids. It's on a hill. There's a 15-degree grade of the hill. What's the magnitude of the force required to keep it from rolling down the hill? So this is going to be answered via the dot product. So there's the force of gravity. That's the weight of the kids on the hill. That's that negative 100 j vector. All right, the vector w right here, this is the 15 degrees. That's the cosine of 15, I sine of 15. That's going to give me the components to get me to that point on the unit circle. So this hill, if you will, this entire hill is the direction of w. So I can cast the shadow of this vector onto that hill somewhere. That's going to be my vector v. And so there's the vector projection. There's the force of the gravity, like pulling those kids on the wagon down towards the center of the earth. That was just in the j position. So w, the x part, the cosine of 15 degrees doesn't matter, because this gravity component just was a 0, negative 100. There was nothing here, so that's why we don't see any cosine in the numerator. So that is the dot product, is just the y component here times the y component of w, which is that sine of 15 degrees. And then the magnitude of w squared is this. Well, w is a unit vector, so its magnitude is 1. The magnitude squared is going to be 1 times w. So this is creating that vector that we saw that was on the hill, that v vector right there. That's what vector we're creating. So there's what we get. This number that's out in front is the magnitude that's pulling that down the hill. Right, the direction is given by this, but we have to pull up the hill. So the opposite of that vector is the direction we have to pull, but the magnitude is what we have to balance out for us to be able to pull it up the hill. So that's the minimum amount of weight to keep that thing from rolling down the hill. Now, if I'm pulling that much force, that 25.9 pounds of force, it's just, the wagon's just sitting there. So that's the minimum amount. I'd have to pull more than that to actually get it to pull up the hill. All right, the last topic in this section is work, computing work. So we're talking about force times distance, and the magnitude of force times the distance AB. We start at point A, we end at point B. So these are what we multiply here. But the force has to be applied along the direction of motion. So again, if this is the amount of force that I'm applying onto a handle, so there's like some handle right here, and I'm pulling in that direction, but I want to move the object this way by the distance, then it isn't, not all of this force is being used to move the object in the direction we want. There's going to be a part of the force that is in the direction, and that's the part of the force that we want. So we end up using the cosine of the angle between these two to get us in that direction. And because cosine is directly involved with the dot product, this is going to end up being exactly the dot product of the force and the direction that we want to move it. So it's always going to be a dot product here that does this. All right, so here we are pulling on the handle like I was talking about before. There's 45 degrees up above the direction that we're moving the wagon. All right, the wagon has 50 pounds inside of it, and we're moving that 50 pounds 100 feet in that direction. Okay, but again, we're not moving it 100 feet in that direction. So not all of that force, not all of that 50, I'm sorry, that's not 50 pounds of weight, that's 50 pounds of force. Not all of that force is being used in the forward direction. So that's the big thing that we're doing here. That's the reason why we're altering it. All right, so there is the cosine of the 45 degrees. It's in the direction that we're moving it. And the direction that we're moving it is 100i. There is no j component. So this part is not going to even play into the dot product. It's just this part that's in the direction times the distance. So it's going to be this 50 cosine 45 times the 100 when we set up the dot product, because we have no, this is our force vector. It does have a j component, but the direction that we're doing, the direction we're moving it, does not have a j component. So we just end up with this part times the 100, and we get the 2500 times the square root of 2 pounds, foot-pounds. So anyway, that is the computational work. It is a dot product. So I could have, from the picture even, just taken the cosine of the 45 times the 50 and multiplied it by the 100 right from there, because it's just the part of the force that's in the direction that we're moving. And since that's adjacent to the angle, that's the cosine of the 45 times the 50 pounds.